Good evening, ladies and gentlemen. Welcome to the DRISMI webinars, the webinars of the driving simulator of the Politecnico di Milano. The Politecnico di Milano has established a new driving simulator thanks to the support of the Lombardy Mobility Cluster. The driving simulator has been launched on last 3rd of February 2021. We have organized a number of webinars. The first webinar was on Industry 4.0 and automotive design process. The second was on intelligent transport system, Industry 4.0 and traffic. The third on green vehicles and lightweight construction, and the seminar of today on intelligent transport system, Industry 4.0 and human-machine interfaces. Today's agenda refers actually to this last webinar in which we will try to find the relationship between intelligent transport system, Industry 4.0 and human-machine interfaces. Let us try to understand actually how this relationship works. When we talk about intelligent transport system, we think of a vehicle with intelligent subsystems that are connected to the environment. And of course, if the vehicle is composed by such intelligent subsystems, of course, subsystem has to be designed, and digital twins of components have to be developed to allow the proper design process of the intelligent transport system, vehicle included. This digital twin, of course, is a paradigm of Industry 4.0. So you may immediately understand the relationship between ITS and I4.0. Since the digital twin of the human is not available, we actually have a driving simulator that allows to derive or to include the actual human in the loop and complete the loop for the design process. Of course, to understand better the perception of the driver, we must record human-machine interfaces data and signals, and this will be the topic of the webinar of this evening. So, today's agenda refers to the presentation of Engineer Del Linz, who will talk about driver monitoring, Professor Caruso, who will talk about the human-machine interface and the laboratory iDrive of the Politecnico di Milano, Professor Gobbi on a number of human-machine interfaces devices, Dr. Fossa on ethics of connecting automated vehicles, and finally we will have a discussion. So I leave the floor to Engineer Del Linz for his presentation.
Okay, so good evening to everybody. Let me just share my screen. Let me know if you see my slides.
Perfect.
Okay, so as introduced by Professor Mastino, these slides we are talking about driver monitoring and human-machine interfaces related to the DRISMI simulator at Politecnico di Milano. The first question is why use Vibrato Telemetry? So why do we need to acquire signals from the driver, active or passive driver? Basically because the new all of us, we know that new technologies will make cars safer and efficient, more efficient than ever. And it's easy to understand that we need to bridge the obstacle, which is the human acceptance of the people to these new technologies applied on the new vehicles. Today, for example, ADS technologies are responsible for basically transition from being the driver is not more a driver, but it becomes a passenger. So all the systems, all the subsystems of the vehicle must be accepted by the driver in the best way. And to reach this goal, it is mandatory to monitor all the human reactions and perceptions, basically acquiring all the signals that we can acquire from the human body, and performing in the same way a lot of tests in a safe environment with a specific, repeatable and a controlled scenarios. That is possible using driving simulators, for example. The VI Grace solution is the following. So basically, we help the customers to investigate and understand the levels of human acceptance of the new driving technologies. And we have designed in the past an innovative set of tools capable of recording, elaborate and post-processing all the human reactions and body responses to a specific driving scenario using a driving simulator. And to define the stress level of the driver, and also from the passengers for sure, Vibrato Telemetry package acquires the following human body signals, which are the skin potential response, SPR, the electrocardiogram, ECG, and also eye tracking signals, thanks to our partner, which is Smart Eye. A brief story on the storyline on Vibrato Telemetry. We started working in 2014 with the collaboration of University of Udine and Policlinico Gemelli in Rome. 2 years later, there was the inclusion of the psychologist team of University of Padova, thanks to Professor Luciano Gamberini. And last year, in 2019, we obtained the CE and FCC IZ certification for the European and North American markets. In this last 5 years, there will be a lot of publications on the international journals like I4.0, Sensor, Measurements, Use Vibrato, and so on. About the human stress level, basically that is related to the activity of the sympathetic and or the parasympathetic division of the human autonomous nervous system. And the first division, so the sympathetic one, is activated when the subject is faced with dangerous or potentially stressful stimulus, and it manages the so-called fight or flight situations. When the sympathetic division is active, among other functions, it increases the cardiac and the pulmonary activity, the sweating, and dilates the pupils. And the second one, so the parasympathetic division, is activated in a stable and rest situations. So when it is active, it essentially decreases the cardiac and the pulmonary activity and increases salivation and the activity of the digestive system. About the first signal acquired by the Vibrato Telemetry package, so the skin potential response, it is acquired from the palms of both hands, and it represents basically the electrical activity of the sweat glands. Its typical shape is reported in the picture on the right, consists in a flat condition when the subject is in a rest situation, so without stress stimulus, while a person peaks when the subject goes to potentially stressful stimulus. In this picture, we can see that we have two stressful stimulus, and that we can see the two peaks in the signal. And to prevent any disturbance or noise due to the mechanical activity of both hands on the steering wheel, and University of Udine a few years ago studied and published an innovative algorithm to remove all the so-called artifact removal noise due to the mechanical activity of the hands on the steering wheel. In this case, we mix the two signals coming from both hands, and we are obtaining one clean signal, SPR signal, which represents in part, the activity of the sympathetic division of the autonomous nervous system. Regarding the other signal acquired, so the ECG is acquired from 3 terminations of a chest vest worn by the driver, and in real time is applied an heart rate variability analysis, both in time and in frequency, performing both time and frequency analysis, and obtaining basically some features related to the stress level of the subject. In particular, here we can see regarding the heart rate variability that an important feature which is the RMSSD. It can discriminate between stressful or not stressful conditions. And the same thing is performed by the frequency analysis, obtaining the features that are reported here, so low frequency, high frequency, and the ratio between the two features. Regarding the Vibrato Telemetry kit, basically it combines a dedicated hardware and software equipment for all this data collection and post-processing, all in real time. And all these components clearly are integrated within all the VI-grade driving simulator solutions, and in particular with the RISMI simulator at Politecnico di Milano. The core of the system is the so-called BioBox, which is basically a small box which is placed in the front of the chest of the driver, and it takes care of the acquisition of the signals and the transmission to the concurrent machine, which performs the real-time elaboration. Together with the chest vest, the driver wants also 2 couples of gelled electrodes on both ends to acquire the previously declared SPR signals. Here we have just 2 pictures. On the left, we have all the components of the kit, while on the right, we have it's represented the 6 termination, the 6 electrodes on the chest vest with halo to acquire the 3 terminations of ECG and the 2 couples of electrodes on the ends. Regarding the real-time analysis and display, VI-grade provides 2 ways to show the real-time elaboration of these human signals collected and computed by the Vibrato Telemetry package, and together with signals coming from any driving simulator, so vehicle dynamic signals and so on. Currently, we support WinTax Pro and iMotions. Regarding WinTax Pro is more oriented on vehicle dynamics analysis or motorsport analysis. It acquires, show and stores all the signals coming from the drive sim, and but have limited post-processing algorithms included. So here in this picture we can see, for example, 3 laps on Mugello track by a professional driver, and we can see that the yellow signal is the SPR stress, computed, as I told before, by starting from the 2 signals coming from the ends. And we can say that, the first lap, in this case, is the more stressful for the driver. Regarding iMotions, is a new software that is has been part of VI-grade framework from few weeks, basically. It is more oriented to a human behavior analysis, not only on vehicle dynamics analysis, and it supports a lot of devices which acquire signals coming from your body. So obviously our Vibrato Telemetry for ECG and SPR signals. It supports a lot 2 eye trackers, which are Smart Eye and Tobii, and also some devices which acquires EEG signals, EMG, and also SGR signals. And it allows the user to integrate digital surveys and questionnaires that could be submitted directly to the subject under evaluation during a test session, for example. And obviously, all the signals are synchronized at the same timestamp, and they can be exported in a simple CSV format, for example. And there are available also some post-processing algorithms within the software. This brief video shows, for example, a post-processing phase of a brief test session drive session on our compact simulator. We can see on the left we have all the signals coming from vehicle analysis from our solver, while in the upper part we can see a camera which reports instant for instant basically where the driver is looking. So the gaze of the driver projected on the screen and also on the dashboard. And just a specification: the use of Vibrato Telemetry kit can be used also on a real vehicle. So if a driver of a real vehicle is equipped with our hardware and software tools, with a simple onboard PC, all the signals can be acquired and streamed to a real-time host receiver. Regarding just the last two slides, future improvements on virtual reality and augmented reality. ViaGrade is collaborating with Vario to add virtual reality and augmented reality within driving simulators. We are working with the XR3 sensor, and in the future, basically, it will no longer be necessary to have a screen and projector, but the graphics all the interior of the vehicle have and of the road will be mixed together to offer a fully immersive driving experience. This small video shows just the use of XR3 visor from Vario, which combines also an accelerometer, which acquires data also from an accelerometer, in order to have the graphic, which is related to the movements of our dynamic simulator, for example. Just to conclude, Vibrato Telemetry will be more and more extensively used for assessing the human acceptance of passive, semi-autonomous and autonomous vehicles. And we are currently available to work with Politecnico di Milano to prepare some focus experiments in the best way to evaluate the interaction between humans, that can be drivers and passengers, and the entire traffic fleet and infrastructures. All the real-time physiological data could be effectively synchronized and compared with all the dynamic state of the simulation subsystems. And finally, the human reaction to critical and risky driver condition could be identified and studied in a controlled, safe, deterministic, and obviously realistic environment provided by the RISMI simulator. That's all, I think.
Thank you very much, Leonida.
Okay, let me just go back to the screen.
Okay, now I invite Professor Caruso to present his contribution.
Can you see my screen?
Yes.
Okay. So my presentation actually relates to the role of driving simulators in user studies according to the various vehicle automation levels that we could have in the next future. What I will present today is are some case study developed in the iDrive Lab, which is a interdepartmental laboratory of Politecnico, where we are studying specifically the interaction between driver, road infrastructure, vehicles, and the external environment. Okay, in this slide, we can see a diagram of a set of subtasks that are either performed by the human or the system for each level of automation. What we can see here is that in level 0 and 1, most of the control tasks belong to the human driver. So in these specific levels of automation, so no automation, the level of the attention of the driver is very important, and evaluating the level of attention of the driver is fundamental for this level of automation. In level 2 and 3, instead, the most critical point is the takeover request. Specifically in 3, we can see the DDT fallback, where the vehicle asks the driver to take the control of the vehicle in dangerous or emergency situation, and it is important to evaluate the reaction of the driver to this request. Finally, level 4 and 5, the engagement of the human driver is more or less eliminated, and the user study should focus more on improving the experience of the user within the vehicle and the overall comfort within the vehicle. So during this transition, the role of human factors is fundamental, and user studies should support this transition in order to reduce human errors, to improve driving the current and the future driving assistance system, to refine or define the driving experience of humans, to increase the overall road safety, and finally to enhance the HMI inside the vehicle, because in the future probably we will have more advanced HMI, and the interaction between the driver and this HMI is fundamental. These studies can be performed in a complete virtual environment, a complete virtual simulation, numerical simulation, by evaluating different numerical or analytical model of driver behaviors by using simulation software, or by using equipped experimental cars for get a real driver's reaction. But surely the most effective way to gather this and to perform these studies is using a driving simulator, where the combination of virtual vehicle and real user may increase the flexibility and the effectiveness of the behavioral studies. In particular, the advantages of a driving simulator is the possibility of control the experimental environment, the high repeatability of the test, and the possibility to check new features of the vehicle under development, and to avoid possible accident. In these studies, as we saw in the previous presentation, specific equipment is required. Specifically, in our lab, we use sensors similar to the one described in the previous presentation, so physiological sensor, a tracker, and we use the specific questionnaire to collect subjective evaluation and possible comments from the subject. So physiological sensor actually allows to evaluate the emotional states and the cognitive states of the driver by using different signals, physiological signals like ECG, GSR, or EMG. The tracker is useful to evaluate the attention of the driver, for instance, by measuring the pupil diameter, or by checking and by monitoring some specific movement of the eye, like saccade and fixation, or to define specific field of interest during the experiment. In relation to the questionnaire, instead, in general, we organize a questionnaire to assess the workload of the driver, the emotion, the fatigue, and the affective factors. Standard questionnaires are are available, like the NASA, Swedish, or self-assessment mannequin, and these are the one that we mostly use during our experiment. In the next slide, instead, I would like to show some of our case study related to specific level of automation of the vehicle. So in level 0.1, we had a specific experiment to evaluate the effectiveness of advanced assistant technologies in reducing fuel consumption. And the aim of this research was to evaluate the cognitive cost of adopting a new driving style for a driver. In this experiment, we involved 24 subjects, and we split the sample in two groups, control groups and experimental groups. The control groups is asked to drive in a normal way along the circuit, and the experimental group is asked to drive with by using the assistant system to keep an optimal driving style. The results show that the assistance system helped the driver to reduce the fuel consumption, but on the other hand, the pattern of autonomic control over time showed that the experimental group, the tendency of the experimental group is increasing the fatigue in maintaining the eco-driving style. And actually, and finally, by using the driving simulator software, we were able to elaborate an ideal eco-driving style to be used as a reference to improve again the assistance system inside the vehicle. Related to the level 2 and 3, instead semi-autonomous driving, here we see a scheme of the function that a human or an autonomous vehicle could do during the driving. And as I said at the beginning of the presentation, the takeover request is as a crucial elements to be investigated to evaluate the effectiveness of this of the semi-autonomous driving of a semi-autonomous driving system. And the aim of this research was to identify possible correlation between driving style and reaction time and using physiological signals to support the vehicle decision. We organized an experiment by developing a specific virtual scenarios where the drivers were asked to drive in a urban area and a highway onto an highway with an automated function, and physiological signals like EKG and GSR was gathered during the experiment. What we achieved at the end, that there is a low correlation between the takeover response and the driving style, and instead the physiological signals could be used for supporting the decision of the vehicle in activating the takeover request. Finally, to move moving the attention to the last part of the graph, so the level 4 and 5 of automation, we start defining the possible new HMIs to increase the trust of the user in autonomous vehicle, because one of the big issue of this system is that the driver could be informed of the reliability of the system installed onto the vehicle in order to trust in in the functioning of the vehicle. And what we did is organizing and clustering the different interaction modalities by function and by importance, and creating, according to this cluster, a specific HMI by using normal and common touch screen or head-up display, but also speech recognition and voice synthesis to increase again the knowledge of the driver about the status of the driver. In this last slide, I would like to show a short video showing the functionalities of this advanced HMI.
Hello, give me a summary of the trip.
So here we can see the voice
control
control that enables some function of the driver of the vehicle, and by using the virtual simulation general virtual simulator, we can evaluate this specific interaction before developing any kind of device for the.
All my sensors are unobstructed and working correctly. Enjoy your trip.
Dropping the windows.
So that's all from my side. Thank you for the attention. If you have any question, please ask me, or now, but probably at the end of the overall presentation.
Thank you very much, Gian Domenico. Now, Professor Gobbi is going to present his contribution.
Okay, thank you, Gian Piero. Let's share. Can you see correctly the screen?
Yes.
Okay, thank you. So, I'll focus actually on two activities that our team has developed, which are actually strongly correlated with Leonidas and Gian Domenico's presentation. The first one is an instrumented steering wheel that is really important because, as we know, the driver interacts with the vehicle by means of pedals, so throttle and brake, and by means of the steering wheel to control the vehicle and obviously to follow the desired path. The loads that the driver exerts during cornering pass through the steering wheel. So measuring this load can be really useful to increase the knowledge of the vehicle-driver interaction, so to develop new driver models, to develop new advanced driver assistance systems, which can take into account this information, and obviously to develop new power steering systems or new devices for detect the driver fatigue level, or, as Gian Domenico already highlighted, to improve the safety and driver comfort, in particular during the transition phases for autonomous vehicles, or during the takeover phases. We have designed a steering wheel which is made in carbon fiber composite in order to maintain the correct mass and inertia with respect to a standard steering wheel. On the steering wheel, we have two 6-axis load cells, which are designed as shown, and are able to measure in real time the free forces and torques acting at each handle of the steering wheel. Inside each handle, we have 3 additional load cells able to measure the grip force of the driver for both the right and the left hand. Overall, we have 18 channels, force and torques that we are sampling at 750 Hertz on each channel. And as already described, the stiffness of the structure is really important, and the first natural frequency of the steering wheel itself is higher than 250 Hertz. In this video, I don't know if you see the video. Probably not.
Yes, we were. Yes, the video was playing.
Okay, it was playing because I don't see the video. So if you see the video, it's fine. You can see to observe the kick plate test. There is the kick plate sliding on the left side. So following the disturbance, the driver is requested to contrast with the steering wheel and to recover and drive in the correct direction. In the top right side of the slide, you see the real-time measure of the forces acting on the steering wheel itself during this maneuver, and the time history is shown on the right side. Usually, this type of steering wheel instrument, there are quite a few described in the literature, are just used on static driving simulators. We have applied this on an actual vehicle. We are planning to use this on the dynamic driving simulator. Obviously, in this case, we need to compensate the fictitious force components due to inertia, weight of the handles, and the effect of the rotation of the steering wheel itself, that obviously generate centrifugal and tangential forces in presence of high-speed action on the steering wheel itself. We are going to get this information directly from the driving simulator in order to get the correct value of the force themselves. We have used the steering wheel actually to analyze different driving behaviors. We have checked simple maneuvers, the response to the kick plate. This is just an example in order to highlight common driving behaviors between different drivers, both during normal driving and during emergency maneuvers. Some specific driving behavior are shown at each line of this table, and some of these common behaviors are really important. As an example, during a panic maneuver, almost all the drivers applied non-negligible loads before the steering wheel rotation. And this information could be helpful in developing new control systems and so on. Based on this type of analysis, we have developed new KPIs for evaluating the steering field. A second activity, again related to what the colleagues have already presented, is a device able to evaluate the human response to external vibrations in an objective way. So it's well known that evaluating human response to external vibration shows very high variability, not only among different drivers, which is called the inter-subject variability, but even for the same subject. So while considering the professional driver, the evaluation of professional driver, we have to take into account this evidence, also while considering a driving simulation. for this reason, we have developed a mechanical mathematical model able to reproduce the acceleration which are actually measured on the contact surface between the human body and the vehicle seat. Based on this human model, a specific mechanical device, let's say the dummy, has been constructed, and obviously this dummy is useful and can be applied to optimize the seat design or to evaluate the performance of seats actually in production, and it can be easily used on the driving simulator. First of all, there are just some results referring to the model that has been developed after a proper parameters identification. You see that there is a very good, reasonably good agreement between the measured vertical and longitudinal acceleration and the output of the model. If we use this information for computing a discomfort index, the K discomfort index, the error is lower than 5%. So we can say we have a validation of this model in the frequency range up to 20 Hertz. Based on this information, the dummy has been developed. There has been a very strong attention in reducing the friction between the moving element inside the dummy. Actually, we have mass which represent the abdominal moving mass, and the damper which is connected to this mass is a magnetic damper that is able to obtain a linear damping characteristic without any friction. So a pure viscous damping, which is adjustable by simply changing the thickness of aluminum plate which is inside this damper, and obtaining a damping coefficient which is perfectly proportional to this thickness. Obviously, we have also validated the output of this dummy. This is comparison dummy and model, and as you can see, the agreement also in this case is quite good. There is some disagreement in some specific frequency ranges, but this is due to the fact that the dummy has non-deformable tights in this version. The plan was to modify it and add deformable tights. So the dummy can be used for evaluating seat. It can be used on the driving simulator for objective comfort evaluation sessions. Thank you for your attention, and obviously, if you have questions, I'm ready to answer.
Thank you very much, Max. Now, let us have a very interesting presentation by Fabio Fossa, who talks about ethics in autonomous driving. And that is a topic that is very much useful for us engineers. Fabio is not an engineer. This is a plus maybe for him and for us as well. So please, Fabio, let us inform about principles and practice connected to automated vehicles referring to ethics.
Thank you for your kind introduction. Let me know if you can see the slides and if you can hear me correctly.
Yes, please. Yeah,
great.
Yes.
So the aim of my presentation today is to give you a quick overview about the work that we are doing at the Politecnico on the ethics of connected and automated vehicles. And basically our aim is to try and translate principles concerning the ethical development of automated vehicles into practice. So to try and find methodologies and tools that might help engineers to develop these enticing new technologies in ways that are conducive to human well-being. So let me start by saying a couple of things about the connections between ethics and transportation in general. So it is very easy actually to see why an efficient transportation system has a positive social and ethical effect. Just think about the social opportunities that we might have access to thanks to functional and effective transportation systems. But of course, as usual, with benefits come also risks to human well-being and to the well-being of our environment. So basically, the most relevant risks in this context are safety risks, so threats to the physical well-being of people, and sustainability issues, of course, as well. We have developed a keen awareness of the impact that our transportation habits have on our planet, and so sustainability is for sure a big issue for future development. And in a sense, autonomous vehicles are an important and enticing technology in this respect, because they promise to possibly solve many of the problems that are connected to traditional driving. For example, autonomous vehicles are supposed to have a great impact on the number of victims on our roads, which is great, and of course, from an ethical point of view, is a great advancement. And also maybe many think that also sustainability will improve thanks to autonomous transportation. But of course, with this new kind of technology also come new risks. There are new risks associated to automated and connected vehicles. For example, privacy issues that might arise from the fact that we need all sorts of data for these technologies to work properly. So we need to be sensitive about privacy issues that might arise. Also, another interesting and quite important domain of risk has to do with the management of risk situation by algorithm. So there might be the situation in which our autonomous vehicles will have to decide how to act in cases where different road users are involved, and so we need to delegate up to a point. We need to delegate this decision directly to the autonomous systems, and so we need to understand which values are important in these occasions, and how to write algorithms that are aligned with our own moral and ethical intuitions and values. Also, responsibility allocation is a huge problem, exactly because we are going towards a situation where the control over the driving function is shared by the user and the machine itself. And so in case of something bad happens, it is necessary to understand how to allocate responsibility between all the subjects and systems involved in order to be able to correct possible mistakes and move toward a situation where responsibility is allocated in a fair and just way. And now, in order to support engineers into facing all these challenges, which are diverse and, well, many actually. The European Commission has released in September 2020 a document with some guidelines, with some recommendations that engineers should follow in order to integrate important moral values into autonomous and connected vehicles. And these recommendations are based on a framework of 7 or 8 principles that we should follow in the design of these technologies. And so the idea is that we need to integrate ethics into the design of automated and connected vehicles. And this is a trend that does not pertain exclusively to this technology, but to actually all new kinds of technology that we are developing. There is a new awareness of the importance of ethics in design in order to build technologies that we can trust. And we already saw the importance of trust for acceptability and so for actually enjoying all the benefits that these technologies might bring us. So it is very important from this perspective to identify and manage relevant ethical challenges during the design process so that we can actually cope with them and try to answer to these difficulties when the technology is still under development and not when the technology is already on the streets in our case. And it is also important to develop methodological tools to put ethical principles into practice. This is a very important point because most of the time principles and recommendations are quite abstract and it is difficult to see how they actually apply to the work on the field. And so it is important to develop tools to bridge this gap. And also, the last part of the research from an ethical point of view is to test innovative solutions, innovative technical solutions to promote ethically aligned technologies. So experimentation is also very important from this perspective, and this is why the simulator will be of great help in this line of research, because it will allow us to research into many HMI-related problems connected to responsibility, to the respect of personal autonomy, for example, or to transparency, to trust. And this is why it would be a great asset to move on with this research and try to get some actual and practical, tangible results in the integration of ethics to the design of our technologies. Thank you. It's all for me.
Thank you very much, Fabio. Now we have time for a discussion. If the people connected to this webinar have any question, we have our contributors here that may answer questions. I have one just to start for Fabio, referring to the comfort as well, to the perception, because actually driving a car for some people is a source of fun. And that might be also an ethical aspect, referring to the fact that if I sit in a car that is just transferring me, translating me from one point to another on the globe, it might be not so fun as driving myself the car. So actually, would you maybe add a comment on the perception and the right that we have to enjoy life that could be cutted by these new vehicles that are just a device that helps in life and maybe doesn't give the pleasure of sitting in a car?
Sure, thank you. This is a very interesting question. And actually, there is a debate about this because this situation brings about a value conflict, right? A conflict between the pleasure of driving, and so the fact that for some people driving the car or driving her own vehicle is a source of pleasure, and so it adds up to their well-being, and which is something positive from an ethical point of view. But on the other hand, there is an argument that associates risks to manual driving and less risk to automated driving. So the value conflict here is between, from a societal point of view, the minimization of harm that is associated with manual driving, but from a personal and individual point of view, the pleasure that one might get from driving his own car or her own car by him or herself. So it all boils down to a factual and empirical thesis concerning the mitigation of harm that might follow from the introduction of autonomous vehicles, and how much it is important from this perspective to have many autonomous vehicles on the road, so to minimize the quantity of manually driven cars on the road. And this is the first part of the problem. The second part of the problem is a political and ethical and social one, which has to do with how a society balance individual rights, individual rights to well-being, and the protection of socially important values like the minimization of victims on the road. Just another quick note on, on the feeling of drivers and in autonomous vehicles. Most of the time, acceptance is not quoted in documents concerning the ethics of connected and automated vehicles. It is seen more as a marketing problem and not an ethical one. I'm not sure if this is correct, though, because acceptance is important to build trust, and also it is necessary. Acceptance, it is necessary for many people to accept these vehicles in order to actually benefit from what they might, the advances that they might bring us. So, for example, for mitigating road victims, it is important to spread the use of autonomous vehicles, but if there is not a high degree of acceptance of these technologies, we won't be able to get there. So acceptance, in my opinion, is very important from an ethical point of view as well.
Thank you. Thank you very much. Are there any more questions?
Giampiero, it's me in my kitchen. I follow very interesting presentation beside Leonida, who is excellent VA-grade engineer, but I congratulate with also Gian Domenico and Fabio, and of course Massimiliano, as very for their very interesting memories. I would say we have a few years experience with this biotelemetry. I don't want to spend too much time, but I have, if I can share my screen, I have a few slides which I can support me maybe with an introduction of this short discussion. So we have done a few experiments in our sim center in the past years. Actually, there are a lot of papers, as Leonida has mentioned, and so we wanted to do some simple scenario. For example, driving in a highway with putting obstacle. How the human would react to this obstacle? How does it recognize the obstacle? At the same time, driving in totally human manual mode or which is possible in a simulator, driving in a totally automated mode. What is interesting in a simulator, you can do without any problem, level 5, let's say, because you don't need really to have any authorization for it. There is total safe. So we wanted to follow this case, and we use our biosignal as Leonida has introduced them, and also we use a questionnaire supported by psychologists with a participant. So we include a few obstacles also because one has to be able to recognize if an obstacle is perceived as difficult or simple, because sometimes, as you will see, human driving through the obstacle is considered easier than having the machine driving through the obstacle. That's very interesting, in my opinion. So we had this type of obstacle presented randomly. Then we apply some technique, and also we apply some methodology for having the obstacle repeated with the support of psychologist. We had the aim of test was also to train an SVM, a simple SVM, which could be used for analyzing the SPR and HEG signals. And I show you some interesting result here. Okay, this is just the time domain skin potential response, a sample of and HEG. And of course, we use a typical technique for extracting the reliability of the test itself with TP, TN, FP, FN as usual. What is interesting to say is that we compute accuracy, sensitivity, specificity, and precision of the test, which I don't have to mention the meaning of to those people attending, of course. What is super interesting, and I think we should look for something like this, how much could we correlate the perception of danger, for example, on a subset of a strata obstacle and the biosignal. This has to be, of course, projected into the driving simulator reality, which is not reality. So the first thing we learn with all this year of experience biotelemetry is to, first of all, to be able to recognize if the human is comfortable on the simulator. If the simulator for him is representative of reality enough to be possible to extend the result that we obtain on the simulator to the real car. Differently, it becomes a pure theoretical exercise. But as you see, not to take too much of your time, but just to give some hints and some stimulation of what could be done. As you see, in this particular case, we always wonder, is it easier to go, and Gian Domenico mentioned that it is easier to go with autonomous driver assisting you, or is it easier to go with manual? So in this simple plot, after we extract the most significant obstacle in this particular case, we see that the autonomous driving is equal or require equal or less. So we call it stress, of course. Stress, it could be identified as the RMS of the SPR, but one can go also the eye rate variability. There are technique the medical doctor are very familiar with that with identifying the variation of frequency of the heart rate, one can say the stress level is going higher or is going lower depending on the parasympathetic or vagal part of the stimulus of the heart, clearly. But just focusing on this, it is interesting to know that, for example, the labyrinth obstacle was perceived as more stressful when we have the autonomous robot driving the car through. Why? Probably because the algorithm that is driving the car through the labyrinth applies trajectory variation, which doesn't appear so natural to the driver. So the entire point of the next, 100 years of autonomous driving technology will be to propose to the driver something that is in line with his expectation. in the way he would drive the car through. Of course, for obstacle avoidance or sudden maneuver, the drive, or maybe lateral wind, in this case not mentioned, the driver would be more than happy that somebody takes care of keeping the vehicle stable. But in other situation where the human mind project the trajectory ahead, how does the robot project the trajectory ahead? It is much less obvious. So I just wanted to give my contribution to this and to tell you that we would be extremely happy to assist in all senses, of course, using what we have packaged in the simulator, but also considering all the result that you want to extract with the simulator with using your own developed technology. And we basically we are in front of an infinite number of questions on this topic. Many more than the typical engineering one, but that's reality for autonomous vehicle.
Thank you very much, Diego. Very interesting presentation. And getting back to my comment that we discussed together with Fabio, I think that the stress is even higher with an autonomous car, and the fun is cut.
Sometime.
So actually, I wonder whether the topic that Giandomenico has introduced, referring on acceptability, is actually will be and even more in the future a hot topic for such kind of vehicle to be actually bought and trusted and accepted by.
I'm driving an autonomous car, semi-autonomous car, and to tell you the truth, when you learn what the robot does, it is so using intelligently the autonomy makes sense, because if I put on adaptive cruise control like in the other webinar while I was answering, and I want to chat, or I feel much more safe with the radar looking ahead, you know. Then, but this is a normal situation. Having always the radar on, when I see that I can go at a constant speed, but for just maybe 1 second of a degree, there is a truck with this corner occupying the passing lane, and the radar out of a sudden becomes prudent and brakes, and the vehicle following me, maybe not autonomous, is wondering, why are you braking? Then, because the radar is decided to brake, then this is a discomfort, you know?
Yes.
So, and I'm driving a Volvo, and the Volvo is quoted the top 3 maybe autonomous sensorization, you know, and still there is much to do.
Yes.
But when I am completely aware of what I'm doing, then I take advantage. The point is, at this time, no level, let's say level 3, you don't have enough information about what the robot is going to do. That is the most critical thing, in my opinion.
Yes.
But on the simulator, we can do everything. And for all the guys developing sensor and actuators and collateral, the driving simulator would be a fantastic opportunity, in my opinion.
For sure, we do agree, and we ask all people that have connected to this evening actually to cooperate with us and go ahead and find new interesting to live vehicle. So if there are not any more questions, I would close here the fourth DRISME seminar. I thank all of you for your contribution, and the meeting is the next DRISME seminars that will be designed and proposed in the future, referring on single topics that we have just introducing this first for DRISMI seminar. So thank you very much, and hope to see you at the driving simulator in Milano. Goodbye.
Sure. Bye-bye.
Bye-bye.
Bye.
Thanks.
Thank you. Bye-bye.
Bye.